Okay, good afternoon, everybody. Let's get started. For announcements, so the Canvas page is up. I think everybody has that because I think everybody submitted their quiz yesterday. Those quiz solutions are posted. So take a look at Canvas under the solutions section, and you'll see quiz 1 solutions there. So if you have any, so your grade shows up, but it doesn't show you which questions you got wrong, but the solutions will show you, compared to your submissions, which ones you got wrong, if any. Tonight, homework 1 is due by 11:59 p.m. So I changed the homework due dates so that, not the due dates, but the due times. So instead of 4 p.m., you'll have till 11:59 p.m. on the days due. That should make things a little less confusing. Let's see. And take a look at the lab. So the lab is posted, the simulation lab, and get started early on that to work through any installation issues with LT Spice or any problems you might have getting started with that. I think that's due this this Sunday. Used to be due Friday. I'm pushing it through Sunday. So for the exam, so this course runs pretty quickly because it's a semester in 4 weeks. I propose holding the midterm exam next Thursday, which I think is 6/11, during the regular lab period. So presumably everybody who signed up for the course had that lab period block free, because that's when you would have been in lab. So from 1 o'clock, it would be a 1-hour exam, but I would give a grace period of 30 minutes. So basically you have an hour and a half, work it for an hour, and then take 30 minutes to try to to get the exam submitted online. And I'll send an email about exactly how that's going to work. So if there's any big problem with holding it during the lab time or at the start of the lab time next Thursday, 6/11, please shoot me an email, let me know. So my office hours will be right after class. So stick around. We'll go offline. I will go offline for a couple minutes. I'll keep the Zoom session up and then join back a couple minutes later. And if you want to ask questions or listen to others' questions, then please do so. So if you have any questions, please shoot me a chat. I have that window up. And if you want to, also unmute if I miss your chat. Otherwise, please stay muted to keep the background noise down. And if I drop off due to technical issues, stick around for a couple minutes and I will be back. I will try to get back. Okay. So let's get started. Let me stop my video here so you can see the whole slide. So you should be able to see the sources slide. So we're going to talk about sources. Sources are the circuit elements that cause a voltage to happen or cause a current to happen. Okay, so they could be something like a battery, but also an AC source could be something like a microphone, right? So that's a source of a voltage or current. So we're going to get specific about what we mean by sources. So a source, when I say source, it means a circuit element that maintains a voltage or a current in a circuit. Okay, and so there are examples of realistic sources: batteries, right, to power things, or power supplies; solar panels, another DC source; battery chargers, that's a source I'll talk about. That's a special kind of current source. Signal generators. So signal generators produce an AC waveform typically, and that's another kind of source. So sources can supply or absorb power. So that's a little weird, right? You think if it's a source, it should be supplying power, but in reality, it can absorb power. And an example of that is a rechargeable battery, right? A rechargeable battery is a source, but it can also absorb power. It can maintain a voltage, but it can also be charged, so it can absorb power. So that's something to remember. A supply example is a solar panel. A solar panel connected to a circuit, powering that circuit is an example of a source supplying power, and a rechargeable battery is an absorbing example, okay? We're going to divide these sources into different types. So there are sources that can provide voltage and sources that can provide current, okay? And then there are also independent sources and dependent sources. Another way to say dependent is controlled. So that source is controlled by something else. Okay, so we're going to have a schematic symbol for each one of these. And so, for example, an independent voltage source will have this symbol. So if you see a polarity marking, plus minus, that's a voltage source. Okay, if you see an arrow with a reference direction, that's a current source. So this is an independent voltage source. This is an independent current source. And then there are controlled sources. So these sources depend on something going on somewhere else in the circuit. They're controlled by some other voltage or current. When you see, again, when you see the polarity markings, that's a voltage source. Right here, this is an arrow, a reference direction, that's a current source. The diamond means controlled. The diamond means that source is dependent upon some other voltage or current in the circuit. So we're going to dig into each one of these a bit, but this is kind of the overview of what we're going to talk about now. So let's first talk about the ideal independent voltage source. So it maintains a specified voltage across its terminals. So its schematic symbol looks like this. So if I have a voltage source, the circle with the polarity, and a specified voltage right next to it, this source at its terminals, these two dots here, this would be connected to maybe to something else. This source would maintain 12 volts across its terminals, right? So from one side of the source to the other, you would measure 12 volts. It's helpful to talk about what, this is a long name for it's 4 words to describe a circle. Let's talk about that, right? Because what it means is that if you connect anything across its terminals, that source, that ideal independent voltage source, will be able to maintain its specified voltage across whatever you connect to it. In this case, circuit element X, right? That could be a light bulb, that could be anything. So it's ideal because it maintains a specified voltage no matter what is connected to its terminals, almost, right? So you could connect something that uses a milliwatt or a megawatt in theory, and 12 volts will be maintained if you draw this symbol. Now, in reality, right, if this is a 12-volt car battery and you try to draw a megawatt from it, that's not going to work. So that's why this is ideal. It's not realistic yet. We'll make it realistic later by adding a resistor. But that's what ideal means. Independent means it's not dependent on any other voltage or current in the circuit. Okay, so this voltage source maintains 12 volts no matter what's going on elsewhere in the circuit. Some good examples are, well, a battery within a normal range. If you operate a 1.5 volt AA battery and draw a few milliamps from it, you will see it maintains 1.5 volts. If you try to turn your car starter with it, it won't maintain 1.5 volts. It's not ideal. But within its normal range, an ideal independent voltage source can be used to model a battery. Another example, an AC source example, is a function generator. So a function generator, you'll see these in electronics labs. They create sine waves and square waves and triangle waves. They maintain, again, within a normal range, a voltage across their terminals. So there are two examples here, a DC source and an AC source. Okay, so this is an ideal independent voltage source. Now let's move on to a current source. So a current source maintains a specified current through itself. Instead of maintaining a voltage, it maintains a current. So here's the schematic symbol. The ideal independent current source is a circle with the arrow. It has a specified current next to it. This source will maintain 5 amps through itself. Well, presumably this current source is connected to something, right? It can't maintain current into nothing. That current has to flow somewhere out of the source and then back into the source. Think of it as like a constant flow water pump, 5 gallons per hour, 5 gallons per minute, whatever. It's constant flow. The pressure may change on both sides, but the flow is constant. So here, the voltage may change, but the current is constant. Okay, and if you connect something to this current source, this circuit element X would have 5 amps maintained through it because there's no place else for this current to go. 5 amps would flow through X. The source is ideal because it maintains a specified current no matter what is connected to it. Again, that it's not realistic yet. We will make it realistic later. But there are many examples within their normal range where devices can be modeled with a current source, an ideal independent current source in a schematic. This source is independent, just like before, because this source is not dependent on any other voltage or current in the circuit. Okay, we'll contrast that with a controlled source in a minute. A good example of an ideal independent current source, again, within a normal range, is a battery charger. So many lead acid car battery chargers maintain a specified current, at least approximately. And so you could see here that if I zoom in, right, this battery charger has a 6 amp setting, there's a switch, and a 2 amp setting. So what this charger does is if you have it set on 6 amps, it will charge a battery with 6 amps. Battery's voltages, when the battery is discharged, pretty low on charge, its resting voltage, right, its open circuit voltage will be, let's say, lower than 12 volts. It's a 12-volt battery and it's discharged, it might be 11.5 volts. When the battery's fully charged, it might be 12.8 volts, maybe up to 13 volts. So the voltage changes, if this is connected to a battery, the voltage changes at the terminals, but this battery charger maintains 6 amps, 6 charging amps into that battery. Okay, so that's a good example. Another good example, if you wanted to use some lab equipment on a lab bench, a power supply, most modern power supplies have a current limit. So you could set the current limit to 2 amps and you could short the terminals together and 2 amps would flow. And then you could start maybe increasing the resistance. And as long as the power supply can maintain a high enough voltage, because that will change, 2 amps is maintained. Okay, so when you think ideal independent current source, think constant or a specified current, not constant, but specified current flowing through itself. Okay. Let's talk about controlled sources or dependent sources. Let's start with a voltage source. Okay, so an ideal dependent or controlled voltage source is controlled by some other current or voltage in the circuit somewhere else. Like you're on one part of the circuit board and maybe at some other part of the circuit board, there's another voltage. That other voltage has some control on this voltage source. So this is the schematic symbol. Again, the diamond means controlled. The plus and the minus mean voltage source. And you'll see specified for this voltage source, I have Vs equals 9 times Vx. So Vx is some voltage somewhere else in the circuit. And somehow, we'll talk about this later, but somehow this voltage source has some connection. It knows what Vx is, and its output will be 9 times that, right, in this example. So at its terminals, it's ideal, so it'll always maintain 9 Vx no matter what is connected to it, except of course a short. If you take a wire and connect, that's a conflict, and You can't define a voltage across a short. So anything but a short, this voltage source can maintain a specified voltage. Okay, an example is an audio amplifier. So think about what an audio amplifier does. It takes an input audio voltage from something like a microphone or an iPhone or a guitar, electric guitar. It takes that voltage and it makes that voltage bigger and applies it to a speaker, right? So that's an example of a source. Maybe the speaker is connected to the output here, and maybe Vx is the voltage at the microphone input. So you might have a tiny little voltage, 0.1 volts at the microphone input, times 9. You get what, something bigger. Did I say 0.1, 0.9 volts on the output? So this is a good example of how to model an amplifier where Vx is the input voltage and 9Vx is the output voltage. So this is a really, it's a practical, it's a practical circuit element to use. So a current controlled voltage source is controlled by current, obviously, right? So both of these are voltage sources. The one on the left is controlled by a voltage. The one on the right is controlled by a current. So this specified voltage is, in this example, 11 times IY, where IY is some current somewhere else in the circuit. So instead of voltage controlling this, it's a current. So the voltage Vs changes based on IY, and a good example is a circuit that we'll actually take a look at when we get toward at the end of the course. A circuit for a photodiode light sensor. It actually senses current and outputs a voltage proportional to that current, so you can sense light intensity. Okay, it's called a transimpedance amplifier. We'll get to that. But this again, it's a useful circuit element to represent approximately a practical source. Okay, so that was a voltage source that was controlled. Here are current sources that are controlled. This is an ideal dependent current source. It's controlled by some other current or voltage in the circuit. So here's the schematic symbol. Remember, diamond means controlled, arrow means current source. And so this current source is controlled by current Ix. So there's some other current somewhere else in the circuit, Ix, and the output of this would be 3Ix. Okay, a good example of this is a bipolar junction transistor. These are common transistors that you can make electronically controlled switches or audio amplifiers out of. And they behave like this controlled current source. And we'll get to this, we'll study this, but the collector current down here, this is the collector current IC is equal to some constant, we'll call it beta, times IB. Okay, so IB controls IC. Okay, so we'll get to that. But this source, like it is, can represent a transistor. A voltage-controlled current source is still a current source. It's just controlled by a voltage. In this case, Vy controls the current. So Vy controls the current Is. So a good example of this is a field effect transistor. So a field effect transistor, it monitors the it essentially senses the gate to source voltage here between these two terminals, and the drain current is controlled by the gate to source voltage. We're not going to get into those. I'll mention a little bit about those during motors, but those are something worth looking into. You can read about them on the internet if you're controlling DC motors, especially those that draw maybe an amp or two or a few amps. Okay, but that FET, that field effect transistor, is modeled well by this voltage controlled current source. Okay, so those are the sources, right? So you have current sources and voltage sources, and you have independent voltage and current sources, right? The circles. And then you have dependent or controlled sources, right? Voltage or current. And they can be controlled, each of those, by either a voltage or a current, okay? So that's kind of the summary slide. This is the big takeaway. You should understand that there are voltage sources, current sources, they're independent or dependent, and the dependent ones can be controlled by a voltage or a current. Okay? All right, so we're gonna go on to a clicker question now. Any questions before I step into that clicker question? Okay, good. And if you were still typing, just interrupt. Feel free to interrupt me on a future slide because I know it takes some time to type in chat and or find how to unmute the microphone if you haven't unmuted in a while. Okay, so here's the question. This is a circuit where two of the circuit elements are well defined and the others, it doesn't matter. They could be resistors, they could be light bulbs, solar panels, it doesn't matter. You have a source here and a source here. And the question is, what is the current IB? So IB is the current through this box, right? And so take a minute and see if you can figure that out. See if you can figure out what the current IB is. Okay, so when I solved this problem, I recognized that there's a current IB that I want to find, and it's the same current. It's along this same branch of the circuit as this current source. So IB equals IS. So that also means that IB equals 4Vx. So we need 4Vx. Okay, let's find Vx. So Vx is the voltage across this this circuit element, and you might either just recognize this, or you might run a KVL equation on this part of the subcircuit. So I recognized, and you may have, that this 5-volt source is maintaining 5 volts between its node on the left side and node on the right side. And that's also the voltage across this, defined across the circuit element. So Vs equals 5 volts. Or you could actually run a KVL equation. I could start here in the lower right and say -5, and then come up here, plus Vx, back to the starting point, don't forget to write equals 0. So -5 plus Vx equals 0, Vx equals 5. Okay, so that's what I did here. I said IB equals 4Vx. Vx is the voltage between this red node and the black node, and that's 5 volts. And so IS is 4 times that. So IS is 20 amps, and that's IB. Okay? Any questions on that? Okay, so now that we have sources, we can talk about Ohm's law. In order to talk about Ohm's law, you need to have some kind of voltage source. So we've got that covered. So you've probably seen this in physics. I would like to reinforce some of the sign conventions and the reference directions for the current and the voltage, and define what a resistor is. So a resistor is actually any device that behaves according to Ohm's law. So let's see. Okay, let me step back a minute. It says, why isn't IS the opposite of IB? IS. Oh, why is it the opposite? Okay. It's not the opposite because the reference directions point the same way through this branch. Okay, so imagine this. I have current flowing where my mouse is, right? That current is flowing at 20 amps. And that current is also flowing at 20 amps this way. So that current is going right to left and then bottom to top. And so since these reference directions for the currents are pointed in the same direction, they're not opposite. If I turned one of these arrows around and they faced the opposite directions, then they would be opposite each other. Okay, does that answer your question? Okay. And if you want to work some more problems like that, stick around. Oh, would the summation be 0? Okay, let's do that. Let's sum the current at this node. So let's sum the currents entering, right? So Kirchhoff's current law says sum the currents entering the node. That's one way to do it. Okay, so I would have IB entering and minus IS entering. So IB plus minus IS equals 0. So IB equals IS, okay? You could also use the form of Kirchhoff's current law that says the sum of currents entering equals the sum of currents leaving, right? So the sum of currents entering is IB, and that equals the sum of currents leaving, IS, okay? Okay, good. Yeah, it's good to ask those questions early because we'll be depending on Kirchhoff's laws and like these sign conventions a lot when we get to more complex circuits. So that's a good question. Definitely ask if you want to talk about these. So a resistor is any device that behaves according to Ohm's law, and Ohm's law, as you've probably seen before, relates voltage and current with a resistance. Okay, so R is resistance in ohms. So if you write your voltage with its reference polarity like this, positive on the left and negative on the right, and you draw the current into the positive side, that's really the important part. You write the direction, the reference direction for the current into the positive side of the voltage. That's what Ohm's law says. V equals IR, right? R is really just a proportionality constant between voltage and current. It means voltage is linear with current. Voltage is proportional with current. And when voltage is 0, current is 0. That's all this is saying. And Ohm is really it's a proportionality constant. It's a volt per amp. We like to name things after people, so we call it and letters. We call it an ohm. So here are examples of resistors. So these are resistors that go on circuit boards, and they on the top left, those are resistors that you bend the leads and they go through holes, and you can put those in breadboards. On the right, these are surface mount resistors. These are more typically used in modern electronics because they're small, and they get really small. They get down to the I've used resistors and they get smaller than this, but 01, 02. So an 0603 resistor is 60 thousandths of an inch by 30 thousandths of an inch, or mils, right? 60 mils by 30 mils. And 01, 02 is 10 mils, 10 thousandths of an inch by 20 mils, 20 thousandths of an inch. So they get really small, and these are actually big resistors right here next to this quarter. Those aren't small. Okay, so that's what they look like. Let's do a little practice with the reference polarity and reference direction. So here is a resistor. I've defined a voltage, and I've defined a current, and I've given a value for the current and the resistance. Okay, so in this case, right, you go look at the diagram in the upper right, I have current drawn into the positive side. That's how I have to have the reference polarity and reference direction in order to use Ohm's law. This matches that, right? This diagram matches that, this resistor. And so it's a direct application of V equals IR. So V1 equals I1 times R1 or 20 volts, okay? If I have another case where I've defined, let's say, V2 to have the opposite polarity, right? Same resistor, same current, same resistance value. Here I have the reference direction pointed into the negative sign of the reference polarity for V2. So I have to do something. I have to do something to get the arrow to point into the positive side of the voltage, right? So I either have to reverse the polarity. I'd have to write plus on the left and minus on the right, and then in the middle write minus V2. Or I have to switch the direction of the current, right? And then write minus 2 amps. So that's what I did. I drew the reference direction in the opposite direction. I wrote negative I2, which is negative 2 amps. And now I have the reference direction pointed into the positive side. So V2 equals minus I2 times R2. Okay, so minus 20 volts. Right? So be sure to, when you're using Ohm's law, pay attention to the direction of current and the reference polarity. Okay? And so, okay, so resistors, what do they do? Resistors, they get hot. That's what they do. They dissipate power. They don't create any light unless you get them really hot, and you typically don't want to do that. And so what good is that? I guess you could use them for heating something. Sometimes that's done. But really what you use resistors for are this V equals IR characteristic. We will see later that you can control the gain of amplifiers with a resistor value. And so that's all based on this Ohm's law characteristic, and we'll get to that. So they are useful. They dissipate power. Let's talk about power calculation for resistors. So if I have Ohm's law applying to this resistor, and then I have P equals IV. So P equals IV applies to everything. It applies to every component. If you have a 2-terminal component, P equals IV works for everything. If you have a resistor, you can modify this a bit. You could say, well, I know V equals IR, so I can plug V, that V into that V, and I get power equals I squared R. So you can calculate power from just current when you know the resistance. I can also take Ohm's law and say I equals V over R, and then I can substitute the I equals V over R into this I, and I get power equals V squared R, V squared over R. So power equals V squared over R is what you can use if you know the voltage and you know the resistance, instead of going through the intermediate current step. These are interesting because this says something. Look at this V squared over R. Let's suppose you have a resistor and you want to dissipate some power, right? Maybe let's say you're draining a battery for some reason, or you're trying to take extra power from a solar panel and dissipate that power somewhere. Maybe heat some water with it. Well, what this says is that if you have a certain resistor with a certain power rating, a power rating is the maximum power that a resistor can handle for a resistor. Let's say it's a 1-watt resistor. If I have a certain voltage across that resistor, right, and maybe the power is a 1/2 watt with a certain voltage, if I double that voltage, the power actually goes up by 4. So you have to pay attention to that. If you double the voltage across a resistor, the power goes up by 4, right? Same thing with current here. So that's a good relationship to know. So a lot of times there are many cases where you would like to know the equivalent resistance of, well, maybe a bunch of resistors that are in a circuit. Let's see, let's go back to the question. So if you increase R, does power go up or down? That's a great question. Look at that. So if you increase R here, power goes up, right? What the heck's with that? When over here, if you increase R, power goes down. Well, It's because voltage is related to resistance, right? So if I go back to this equation, right? If I increase R, right? If I increase R, my current goes down, right? So my current goes down. So if I increase R here, right? For constant current, my voltage goes up. And in fact, here's what we're going to see at the end of this lecture, as long as we can get to the last topic, if not next time, that when you connect a resistor to a circuit and you change that resistor, let's call that resistor a load resistor. It's just a resistor that's absorbing power. You connect it to a circuit and you vary that resistance, right? From something really low, a few ohms, to something really high, a few k ohms. There's going to be a point where you get maximum power transfer, and we're going to talk about that. So for a given circuit, if I increase resistance, power might go up. For another circuit, if I increase resistance, do the same thing, power might go down. Okay, so we're going to take a look at that in a minute, but that's a good question. So keep that in mind until we talk about maximum power transfer. Okay, so there are many cases when you would like to know an equivalent resistance. Either you have many resistors in a circuit and you want to combine those into a single equivalent resistance, or you have a circuit with many different circuit elements, not just resistors, but that circuit behaves like a resistor. In other words, it behaves like Ohm's law. So you can take any circuit that behaves like a resistor, right? That means it follows Ohm's law based on voltage and current between two terminals. And you can create an equivalent circuit that has the same I versus V relationship between those terminals, right? So you can make that circuit as simple as a single resistance, and that single resistance would be the equivalent resistance to this bigger circuit. So I have this big circuit, lots of components in it. It behaves like Ohm's law, but from the outside world, since it behaves like Ohm's law, you could treat it as just a single resistor REQ. And so what we're going to look at is how do you do that? How do you figure out what REQ is of this bigger circuit so that you can model it with just a single resistor? Okay. You could do this. You can apply a voltage and measure, calculate, simulate the current. Okay, so I apply voltage, 10 volts, and I measure the current, 2 amps. I simulate the current, 2 amps. That would mean you have a 5 ohm equivalent resistance, right? So, or you can apply a current and measure or calculate the voltage or simulate the voltage. Okay, so apply I and measure V or simulate V or calculate V. So then the equivalent resistance is V over I. That's just Ohm's law, right? So if I apply a current 3 amps, right, and I get a voltage 30 volts, then I have a 10 ohm equivalent resistance. You just calculate the equivalent resistance based on Ohm's law. That has to be a circuit that behaves like a resistor, right? So it can't be some other circuit that is nonlinear. It has to behave like a resistor. Okay, so let's do this for some specific cases. And again, this might be something you've seen in physics, but it helps to kind of look at it again or just go through it so that you could see some circuit analysis techniques. Let's suppose I have series resistors, R1, R2, R3. Whenever I say, it's funny, whenever I say the word series or I say series resistance, I either get my iPhone answering me or Alexa answering me. In fact, when I'm in a live classroom, when I start talking about series resistors, several people's iPhones start Siri responds instead of series. Siri. Anyway, sorry for the digression. So let's suppose I have 3 resistors, R1, R2, R3 in series, and I would like to know the equivalent resistance. And you probably know the answer, but I would like to be able to replace those 3 resistors either in the real world with a single resistor or just for analysis to make the problem easier. Okay, so this is the voltage, this is the same voltage on the right, this is the current on the left, this is the same current on the left. I want to find Req for those series resistors. So we just talked about how to do that. You use V and I, and you set, well, Req is equal to voltage divided by current. So let's find some equation, some expression that has V in it, it has I in it, and then we can rearrange that expression to be V over I, and then get our answer. That will be Req. So that's our goal. Our goal is to have some expression where we can get V over I on the left, and on the right will be the equivalent resistance. Okay, so let me define some voltages across these resistors. V1 across R1, V2 across R2, etc. Now let's just write an equation. Let's start by writing a KVL equation. And so if I start at the bottom here, let's do a KVL. Minus V, right, plus V1 plus V2 plus V3 equals 0. Okay, so that's what this is up here. Rearrange that, I get V equals the sum of the voltages. Okay, now if I introduce Ohm's law, V1, right, if I want to substitute something into this equation that has an I in it, remember I need V over I, so I need an I somewhere. I can get an I into this equation by saying V1 equals I times R1, right? That's Ohm's law for this resistor. Likewise, that same current goes down through resistor R2, and I can say V2 equals I times R2, right? I is coming down, and V3 equals I, that same current, times R3. Okay, so now let's plug these together. Let's put this V1 into this variable up here, right? Combine those, and you get the voltage is that sum of Ohm's law terms. And let's factor out an I. Okay, why did I do that? Now, because I can say V over I, this is what I'm looking for, V over I, is R1 plus R2 plus R3. So we've proven what you've probably seen before, but again, it's good to have a basis for it, that resistances add in series. Okay, so if you have series resistors, not just 3, you could have 10, you could have 2, you could have 100. You add all of those resistors together, the resistances together, to get the equivalent resistance. If I put the left circuit with 3 resistors in a box, and I give you a voltage source, I give you a power supply and a multimeter, and I put this this resistor on the right into a different box, and I give you the same equipment, you wouldn't be able to tell the difference between those two. Okay, so looking at voltage and current, so that's why they're equivalent. Okay, so let's do the same thing for parallel resistors. Here's how we would analyze parallel resistors to figure out the equivalent resistance. So on the left, we have 3 parallel resistors. I've defined a voltage across the terminals that connect to those parallel resistors and a current into that parallel set. Right. On the right, this is the equivalent resistance I would like to find. So let's do the same thing. Let's find an equation that has V in it and I in it, rearrange it so that that equation has V over I, and that's the equivalent resistance. I'll define these currents, I1, I2, and I3 down through these resistors so that I can actually do a Kirchhoff's current law equation. So at this top node, if I sum the currents leaving that node, right, negative I1 is leaving, or negative I is leaving, that's what this negative I is. Positive I1, positive I2, positive I3 are leaving. So I sum all those together, set those equal to 0, rearrange it a little bit, and you get I equals the sum of those currents. Okay, and then let's introduce Ohm's law. So here's Ohm's law. If I know the current I1 and I know the resistance R1, then I know the voltage, right? This voltage, V, is the voltage between that entire top node, right, and that entire bottom node. That's one reason we consider nodes the entire connections, the whole connection between circuit elements. Voltages are defined between nodes. So this V is between that whole top node at the positive side and this whole bottom node at the negative side. We can continue with Ohm's law, and so that means that V is also equal to, well, you know, V is applied also across R2. So V is also equal to I2 R2 and I3 R3. Okay, and so we can combine these two together, solve for I1, solve for I2, solve for I3, substitute into that left equation there, and you get this. So now I have an equation that I wanted. I wanted an equation with V and I, and so now I have I equals V times that. And so I get I over V, which is actually the reciprocal of equivalent resistance. I invert that, and I get this. REQ equals 1 over this. Written a little more cleanly, you get this. So REQ equals 1 over the sum of the reciprocals of the resistances. Okay? So that's how you find REQ for parallel resistors. You could have 4 resistors, 10 resistors, 2 resistors. Just put the reciprocals of your resistors in the bottom here. Okay? In your book and some, you know, on the web, you will see an equation for a parallel pair of resistors when there are only 2 resistances. For example, if there were just R1 and R2, the equation, you could rearrange this equation to be R1 plus R2 over, I'm sorry, R1 times R2 over R1 plus R2, right? So you could write a different equation. I actually recommend not doing that because that only works for 2 resistances. So if you have 3 resistances, you have to do an intermediate calculation and add and combine resistances one at a time. It's a slower way, and it's also prone to error because I've seen mistakes where folks will try to apply that multiply over add formula. I'm not even showing it here. I don't want to even get it in your head, but they'll apply that to 3 resistances, and it's just you get the wrong answer. This always works. This equation always works no matter how many resistances you have. If you have 4 resistors, just add plus 1 over R4 in the denominator. Okay, so I would recommend using this. Okay, so this reciprocal of resistance shows up every once in a while, and sometimes it's convenient to work with the reciprocal of resistance. And we actually have something defined that is the reciprocal of resistance. It's called conductance. So G equals 1 over R. G is conductance, and it's in units of Siemens, abbreviated with an S, or units of mhos, which is ohm spelled backwards and then pluralized. So, and there's an upside down omega there. You'll have to search for the alt code for that one. So a conductance is just the reciprocal of resistance. So if I have a 4 ohm resistor, it is equivalent to saying that is a 0.25 mho or 0.25 Siemens conductance, okay? And it just sometimes that's convenient. These both mean the same thing for that resistance. And so, for example, if you have parallel resistors, this is what we saw on the previous slide, right? If you invert both sides of this equation, you get the equation for the equivalent resistance for parallel resistors. If you convert these to conductances, you see that for parallel resistors, right, the conductances add, right? So conductances add in parallel. So it's not much different when you're typing this into your calculator, but It's just something to know that there are some cases where it's convenient to work in conductance. So that's what conductance is. Okay, so so let's do this. Let's start looking at ways voltages and currents behave in series and parallel resistor circuits. Okay, there are a couple special special cases of resistor circuits. One is the series circuit, and there's a parallel circuit we'll look at next. And there are, again, many cases where you would like to know, given this voltage across all of these resistors, the set, what are these individual voltages? Okay, now you could calculate it. You could figure out the equivalent resistance and then apply the voltage and figure out the current and use Ohm's law on each one of these. There's a faster way. Because this shows up so often, there's a faster way to do this. It's called voltage division. And so voltage division is a way to calculate how voltage divides among resistors. And by divide, I don't mean by like divided sign. I mean splits up. So if you know the voltage across this whole series set, voltage division is a way to tell you, for you to calculate how the voltage splits up into V1, V2, and V3. So given V, find V1. That's an example. For parallel resistors, there's a sort of a dual to this approach. So sometimes, many times, when you have a circuit like this, you would like to know, how does the current divide up among these resistors? Okay, and so that approach is called current division. It's a way to calculate how current splits up among parallel resistors. So for example, given I, the current into this parallel set of resistors, what's I1, or what is I2, or what is I3? Okay. Okay, so let's work on voltage division first. Let's figure this out. Again, I think you'll wind up using this, so it's worth running through the derivation and then definitely remembering, writing down, using the results. So let's suppose that you have a voltage V1 across R1, and you want to well, let's derive the voltage division equation so that you only have to do it once and then just apply the approach. So let's use Ohm's law and define a current into this series set of resistors. And so V1 equals I1 times R1, right? So that's Ohm's law for this resistor. But you could also say, well, I could calculate the equivalent resistance of these series resistors and then apply Vs to that equivalent resistance to figure out I. So here's where that comes from. Vs, right, this voltage, divided by the whole equivalent resistance, R1 plus R2 plus R3, equals I. So these are two, we can get two expressions for I. Right, so if you plug this I into the equation above, you get this. You get V1 equals Vs times this ratio. Let's take a look at this ratio. This shows up over and over again for series resistors. The voltage across V1 is equal to the voltage across the series set, right? The whole series set, that's its Vs, times the ratio of, on top, the resistance across which you're trying to find the voltage, divided by the sum. Okay, so that's why R1 goes up here, and then all of the resistors go in the denominator as a sum. Okay, so in the same way, calculating V2, right? You could run the same equation, same derivation up top, but you get the same thing. V2 is equal to the voltage across the series set times the ratio of, on top, the resistance across which you're trying to find the voltage, divided by the sum of all series resistances. Okay, so then V3, in the same way, V3 is Vs times the resistance across which you're trying to find the voltage, divided by the sum. Okay, so you can apply that to series resistors in order to to find voltages. And this works for 2 resistors, 4 resistors, 100 resistors. All you change is in the top is the resistance across which you're trying to find the voltage, and the bottom is the sum of all of your series resistors. Okay, so that's voltage division. Let's talk about current division. So current division is going to describe how current splits up among parallel resistances. Okay, so let's derive an equation for the value of I1 if you know IS and all these resistance values. So Ohm's law would say that the voltage from top to bottom, right, the voltage across all of these parallel resistors is described by Ohm's law. So I1 equals V over R1, okay? And then also by Ohm's law, if you take all of these resistors, combine them into an equivalent resistance, you get V equals IS times REQ. So REQ is the combination of all these resistors. Replace those with one resistance, and then you have V equals IR, right, with those values. Okay, so this, right, is equal to IS times the equivalent resistance. Here's the equivalent resistance of those 3 parallel resistors. So what I can do is I can write this up top here. This is the expression to remember for current division. It looks a little complicated, but you'll see in a second, it's actually pretty easy to remember. I1 equals the current coming into the parallel set of resistors times the ratio of 1 over the resistance through which you're trying to find the current, divided by the sum of the reciprocals of all the resistances. Okay, so that pattern repeats itself. In the same way, to find I2 is equal to the current coming into the parallel set times the ratio of 1 over the resistance through which you're trying to find the current divided by the reciprocals of the sum of the reciprocals of the other resistances. Okay, same thing for I3. So this is current division. When I say current division, this is what I mean, applying this approach to resistors to find the individual currents. You could work with conductances here. If you don't like the reciprocals, this could be G3 over G1 plus G2 plus G3, right? That's an alternative if you wanted to work like that. Okay. Okay. So there's one more topic I want to cover before we take a break, and that is a topic closely related to voltage division, and that topic is potentiometers. So potentiometers, also called a pot. So if you say turn the pot on the board, it's a potentiometer. It's a 3-terminal adjustable resistor. Okay, and so usually it has a knob or a slider. Some have sliders, many of them have knobs. So you turn this knob and it adjusts resistors. I'll show you this inside this device. You turn this screw and it adjusts the resistance. The same thing with these knobs. These look like volume. This looks like a volume knob here, right? With the knob taken off. So here's what a potentiometer schematic symbol is. And so what you'll see, it's a 3-terminal device. It has A, B, and W as terminals. And it has a value, RP. That's going to be a value in ohms. And I'll show you what that means. So as a cartoon, but really, realistically, you could make one like this. In fact, this volume control knob looking device is probably built like this. Here are the 3 terminals on the bottom. So between A and B, you'll notice, so A and B have, consider these wires connected here. In fact, let me blow this up a little bit. So A and B are terminals where you could connect wires, and this is a wire going up to some resistive material. this resistive material is on maybe a flat circuit board, right? So it's just resistive material, and then there's a conductor on the other side that goes down to B. So that resistive material between here, right, A and B, is actually what this RP is. We'll get to that in a second, but RP is the value of the resistance if you were measuring between A and B, okay? So then there's this W terminal, and this W terminal, it's drawn here as a cartoon. When you turn the knob, this is what turns, and this is a wiper. So this wiper wipes along this resistive material. It makes contact with it. So it changes the position at which W makes contact with the resistive material. Okay, so if you have W in this position, between A and W, you have, I don't know, roughly a third of the resistance, a third of the resistive material there. So you would have roughly a third of the value of all the resistance material showing up between A and W. You'd have 2/3 of the value of the total resistance between B and W. Okay, let's take a look at that a little deeper. So here is a potentiometer. I've given it a value of 10 k ohms. Okay, and so in the lower left is the same cartoon. What I'm going to do is actually represent this potentiometer as two separate resistors. So because right between A and W, there is some resistive material, and between W and B, there is some resistive material. And those values can change as you change the wiper position, okay? So the resistance values, R1 plus R2, right? The resistance between here and here, plus the resistance between here and here, is the total resistance. That's where this comes from. RP equals R1 plus R2. Let's define T as the fraction of the full turn range, okay, from 0 to 1. It's just a factor. It's just saying, when I turn the knob all the way to the left, I'm going to call that T equals 0. When I turn the knob all the way to the right, I'm going to call that T equals 1. It just defines the position of the knob, right, of the potentiometer. And so let's build a table of resistances. And to do that, we're going to use the value of resistance R1, right? So if the total resistance is RP, you multiply it by this fraction in order to get R1 value. And you multiply RP by 1 minus T to get the R2 value, okay? And let's create that table. So for a given T, I get a given R, I get an R1 and I get an R2. So if T is 0, in other words, this wiper is directly connected right to that terminal A, that wire right there, I'm going to have 0 ohms between A and W, which means R1 is 0. And between B and W is, well, all of the resistive material. If I turn the potentiometer a bit, let's say 1/3 of its way, I will have 1/3 of the resistive material, or 3.33 k ohms, right? That's RP times T, between A and W. And then between B and W, I have 6.67 k ohms. Okay, and then likewise for halfway, if I turn the knob halfway, I have half the resistance for R1, half the resistance for R2. And if I turn the knob all the way, now W is touching B, so there's 0 ohm resistance between W and B, 10 k ohms between A and W. Okay, so that's what a potentiometer does, right? So it's a variable resistor circuit, and you can use these for volume control knobs. You can use these for adjustable voltages, for example. Okay, and that's what I want to talk about next. But do you have any questions on the potentiometer?
I have a question.
Yeah.
So for a potentiometer, would that mean that R1 dictates how resistive the how resistive it is? Does that make sense?
Yeah. Well, that's a good question, because a resistor has two terminals, right? And this has 3 terminals. So if you wanted to create an adjustable resistor, you could connect A and W to your circuit and just leave B alone, just not connect B. And then you would have a resistance that varies between 0 ohms and 10K ohms, right? Now, that would be if you want 0 ohms when you turn the knob all the way to the left, I would use R1. If you, for some reason, wanted 0 ohms when you turn the knob all the way to the right, then I would connect B and W into your circuit, because when the potentiometer is turned to the right, you get 0 ohms. So you could choose, right? So you could use either one of these resistances as just a variable resistor. Okay, does that answer your question?
Yes, thank you.
Okay, and it's common, and you'll see in one of your, it's either a quiz or a homework problem, it's common when you just want a variable resistor, let's say you want resistance R1, you want that to be your variable resistor. It's actually common to take W and connect it to B with a wire, and that actually takes R2 out of the circuit. You have 0 ohms in parallel with R2, and then only R1 controls the resistance from A to B. And you'll see that in a problem coming up. Okay. And so, okay, and there was a question about how useful is it because equivalent resistance won't change. Was that about this problem here? Was that about the potentiometer? Okay, how useful is it? So I'll show you a use. So it's equivalent. Its resistance from A to B doesn't change, but its resistance between A and W and B and W changes. If you connect a wire between B and W, then between A and B, you'll see in a problem that R1 then controls the resistance between A and B. Let me show you a practical application of this and really why you need the 3 terminals. So you can create an adjustable voltage using a voltage source and a potentiometer and all 3 terminals. So here's a 12-volt source, and I have a V out, and I'm going to show you that V out can range based on turning the knob between 0 volts and 12 volts. You could also think of this as maybe the input. Maybe this is from a microphone, and you want to control the signal coming out of this microphone circuit before going into an amplifier, so you could control its volume. So this circuit would also let you use a potentiometer to scale down, to turn down the volume from a microphone if this were a microphone. But here, let's use a DC source to create an output that's adjustable. So let's do this. Let's draw in the model, the 2 resistor model of a potentiometer. And look what I have here. I have a voltage divider, right? I have a voltage applied across series resistors, right? R1 and R2 are in series because if I have current flowing down through R1, it also flows through R2. Now you could argue, wait a minute, what if I connect something to this output? That's true. If you connect something that has a resistance anywhere close to R1 and R2, then these are no longer in series, okay? But if whatever you connect out here looks like a very large resistor value, let's say 10 times, 100 times bigger than these resistances, then still the current flowing down through R1 is still approximately the current through R2. So these are in series. Okay, so since these are in series and I have a voltage applied across, I can use the voltage division expression. So V out, the voltage across R2, that's what I'm looking for, equals Vs, the voltage across the series set, times R2, the resistance across which I'm trying to find the voltage, divided by the sum of the resistances. Okay, so that means that if you look at this, right, R1 and R2 range from 0 to RP. So in the bottom here is just RP. R1 plus R2 is always constant. It's 10K ohms. R2 varies, as we saw in the prior slide, between 0 and 10K. So you get this ratio here that goes from basically 0 to 1. And so as you turn the potentiometer over its full range, the output voltage will range from 0 to Vs, 12 volts. Okay, so this is a way again, this is a way to create a volume control, create an adjustable output voltage using a potentiometer, and it's a practical use of all three terminals. Okay. All right. Let's do one more thing and take a break. All right, let's exercise your brain before the break. Here's an Ohm's law problem. See if you can figure this out. Take 30 seconds and answer this. You have a circuit element A, don't know what it is, but you know 4 amps is flowing from left to right, and you have a voltage Vy defined across a 12 ohm resistor as shown. Oh, so these, someone had asked how to submit clicker questions. Actually, so there is no clicker. I haven't, if anybody knows a way to do this remotely, I'd love to know. I didn't find a way to do it, but so you, as far as I know right now, you cannot submit clicker answers. So this is for you to write down on a piece of paper, make sure you know how to do this. I'll show you the answer. If you don't know how to do this, ask questions or see me at office, talk to me at office hours. Okay, so here we have, I have IA, the 4 amps, going into the negative side of Vy. So I want to turn that around and have an arrow. I want to have the reference direction for the current drawn into the positive side of Vy. I can do that by flipping the arrow and putting a negative sign in front of the current. That's what I've done here. And so now this is a direct application of Ohm's law, so I get negative 48 volts. Okay, questions on that? Okay, well this is a good time for a break. Let's take a break now. It's my clock says 5:14 at this point. Let's round up. Let's say that let's take a 10-minute break so that at 5:25 let's resume. So I will keep the Zoom session up, and we will resume the class at 5:25. All right. So I'm going to hit mute now, step off for a second. So go ahead and stretch your legs, and I'll talk to you then. Okay, so let's get started again. Can someone give me a sound check? Yeah, resume. Did someone get that resume joke? So can someone confirm that they can hear me? Great, thank you. So the next topic I would like to talk about is node voltage analysis. So this is the point at which we're probably getting into some new material compared to what you talked about in physics. Maybe you talked about this, maybe not, but it's worth going through, and it's worth talking about. Node voltage analysis covers two things. One, it covers what node voltages are, and it also covers a systematic way in order to calculate voltages throughout a circuit that have resistors and sources, dependent or independent. So let's walk through this. And so what I have to do is I have to define a node voltage. A node voltage is the voltage between a node and a reference node, right? Voltages are always measured or defined between 2 points. So there's some node, and then there's another node we're going to call a reference node. Okay, and the positive side of that voltage is going to be at the node, and then some other node that's called the reference node will have the negative sign. The reference node is the negative side of the polarity for every node voltage defined in the circuit. It's often called ground. Okay, so if you you know, connect the negative lead of the voltmeter to ground, this is what that means. Okay, this is ground. Traditionally in power systems, for example, just residential power systems, the ground is actually connected, like the earth ground is actually connected to ground, the ground wire. But in many of our circuits, it's not, but we still call it ground. Okay, let's take a circuit. Let's take this circuit with a current source and a few resistors, 5 resistors, and let's analyze this. Let's talk about the circuit. I want to define one of these nodes, one of the nodes of the circuit, as ground, as a reference node. And so I'm going to define the bottom. Now it doesn't have to be the bottom. It can be any, you can use any one of the nodes to be a reference node. I'm going to choose the bottom node. And so that whole node, right? Remember, the node is the entire connection between circuit elements. That whole node is considered the reference node. This ground symbol, all it does in this circuit is designate that's the reference node. It's not a component. It doesn't really do anything other than say that's the reference node. Okay, so then I can define a node voltage, V1. So what I do with node voltages, I write them somewhere in proximity close to the node that I'm defining to have that node voltage. So V1 applies to this whole node here. Okay. Remember V1, this node voltage, I haven't shown any polarity on this. Every other voltage I showed prior to this had a polarity. That's because this polarity is implied. A node voltage is the voltage between this node, this pink node, and a reference node, the blue node, where the positive sign is at the pink node and the negative sign is at the blue node. So V1 is between the pink node and the blue node with that polarity. Okay. Okay, so let's define node voltage V2. I just picked a node and I call that V2. So that applies to this entire center node here. And it is the voltage, if I were to explicitly draw the polarities, write the polarities here, it would look like this. I'd have V2 between this node with the positive side and the reference node. The reference node always has the negative sign of the node voltage. And so here's V3 that applies to this node. And you could guess V3 has this voltage, positive sign at this purplish node, negative sign at the blue node. Okay, so you can think of it this way. The reference node, if you were measuring voltages, right? You have a voltmeter, it has a black lead, it has a red lead. The red lead's positive, the black lead's negative. That's how you measure the voltages. We talked about that. The reference node is where you would connect the black lead all the time if you're measuring node voltages. You'd always touch the black lead to the reference node, to the ground, if you were measuring node voltages. And the non-reference node, right, where you've defined node voltages, is where you connect the red lead of your voltmeter. So what you're doing is you're just measuring node voltages like this. It's the voltage between those two nodes. So if I wanted to measure voltage V1, node voltage V1, I would do this with a meter. I take the red lead, put it at V1, the black lead, put it at the reference node, ground. If I want to measure V2, I do this, right? Red lead at V2, black lead at ground. Same thing with V3. Okay, so that's how we define node voltages. It's like saying you have a voltmeter in your car and the chassis of the car, all the exposed metal connected to the frame in the car is connected to the negative side of the battery. We typically call that ground in a car. And if you want to probe around on different wires and check the voltages, you would be measuring node voltages if your negative lead is always connected to the chassis, touching metal on the chassis, and you're probing around elsewhere with the red lead. Okay, so there's nothing special about the reference node, its location. you can change it. There are conventions like the earth for power systems, and usually like you'd want usually to find the case of like a computer that is usually ground. You don't have to. There are some conventions though. But let's move the ground node. So this is the circuit we just looked at. Let me move the ground node. Right, here's the same circuit, but I'm going to move the ground node to the upper right. When I move that ground node, I didn't change anything. The circuit, like all the currents throughout the circuit, all the voltages across the resistors, they didn't change. All I did was I designated where you would touch the black lead if you were to measure node voltages, or where you're defining a reference to define node voltages as variables, right? So I didn't change anything. I didn't change any connections. All I did is I put the symbol here and I said, that's the reference for all of my voltages. Okay, so that entire node now is ground. That is my reference node. So I'm going to define different node voltages because I've changed the reference. The node voltages are different. So this V1 prime really isn't related to V1 other than it's kind of in the same spot. And that applies to that node. And V1 prime is actually the voltage, right? It's the voltage between the upper left node, the pink node, and the purple node, right? In the left, when I had the reference node at the bottom, V1 was over here across a resistor. If I change the reference node, even though V1 prime is at the same node as V1 was, I've changed the reference. So you're actually measuring, defining a voltage at a different place in the circuit. Okay, so V2, I'm going to put that in the same, V2 prime, I'm going to put that in the same position as V2. But now that voltage, right, is between V2 and ground, the positive sign at the V2 node and the negative sign at the ground node. Okay, and now what do I do with V3? Well, I'm not going to make it the upper right corner because that's now the reference node. Let me put it down at the bottom. So that entire node now has a node voltage defined as the voltage between blue and purple with that polarity. Negative always goes at the ground side, right? When you're measuring node voltages. And you know, I think I've emphasized that V1 is not V1 prime, V2 is not V2 prime, V3 is not V3 prime. Okay. And the question is, what is the arrow in the circuit? So the arrow, this is the current source. So this is an ideal independent current source. Okay, so that's what that is. So this is assuming we have resistors and a current source in the circuit. This is, so back from when we talked about sources, this is the second source we talked about. Okay. So adding a reference node does not actually change the circuit. It only indicates what node you were using as a reference for measuring voltages, as the negative sign for your node voltages. And changing the reference node doesn't change voltages across these individual resistors. It doesn't change any currents through the circuit. It doesn't do anything. All it does is change where you're measuring or where you're defining voltages. Okay, so the circuit still operates as normal. It doesn't change. You're just moving the negative probe to someplace else in the circuit. Okay, so that's those are what node voltages are. And so what I want to do now, so now we're going to step into node voltage analysis. So node voltage analysis is this. Let's just look at the left circuit here. Node voltage analysis says, if I know this current source, 3 amps or whatever, and I know all of these resistor values, what are the values of node voltages V1, V2, and V3? Okay, so find V1, V2, V3 given everything else is known in the circuit. That's what node voltage analysis is. So what I'm going to show you next is one step in that direction. It's both a step in that direction and a motivation for using node voltage analysis. Because after you solve for node voltages, you are only 1 or 2 steps away from all other circuit variables. So you're gonna do node voltage analysis. It's basically simultaneous equations. and you're going to get all the node voltages. And then if you want to know a current through a resistor, or the power for a resistor, or the voltage across a resistor that's not connected to ground, you can do it in 1 or 2 steps, easy steps. So, so let's take this circuit. We're going to work with this circuit. And what I want to do is isolate this little portion of the circuit here and look at Vx and Ix. So Vx is not a node voltage. It's just the voltage across this resistor. I'll show you it's related to V1 and V2. And Ix is just a current through this resistor. And again, I'm going to show you that you are like a step away from calculating power and current once you see the node, once you know the node voltages. And also, this is going to show you a way to write equations for node voltage analysis just by looking at the circuit, okay? Just by looking at this. I'll show you what I mean. Let's isolate this portion of the circuit. And I'm going to break this out over here. And so now we have just this resistor. So this resistor is still in the circuit. It has a voltage on the left, a voltage on the right, node voltage, and a resistance value. I'm just concentrating on it. So I'll write my values that I have on the left, write them on the circuit. And so what I want to do is let's figure out what Vx is. Because if I know Vx, then I can figure out what Ix is from Ohm's law, Vx and R1, right? Let's use Kirchhoff's voltage law to figure out what Vx is. Now, V1 is actually explicitly written like this, right, with polarities. V2 is written like this with its polarities between the node and ground. And so I could write a KVL equation around this that says minus V1 plus Vx plus V2 equals 0, okay? So that's the KVL equation. This lets me solve for Vx, right? So if I know my node voltages, V1 and V2, let's say I solved for them through node voltage analysis, then with one step, I can figure out the voltage across that resistor, okay? So Vx with its positive side on the left associated with V1 is equal to V1 minus V2. We can use this using Ohm's law to figure out what Ix is, okay? And so Ix is equal to Vx over R1, which is V1 minus V2 over R1. I put a circle around this, or a rectangle around this, because it's important. This is what you're going to use for node voltage analysis when writing your equations. And here's what it says. It says the current leaving from V1 to V2, right? That's what Ix is. The current leaving from V1 to V2 is V1 minus V2 over R1, right? From V1 to V2, V1 minus V2 over R1. So let's kind of put that on hold along to the side, and let's then calculate the voltage and the current with the opposite polarity and the opposite reference direction, respectively. I can break that resistor out again out of the circuit, define Vy and Iy, and then define V1 and V2 explicitly. And then I can write the KVL equation. So KVL, right, minus V1 minus Vy plus V2 equals 0. My goal is to figure out Vy first. Vy is V2 minus V1. So if you know V2 and V1, then you can figure out the voltage with the opposite polarity compared to Vx, right? And then I can use Ohm's law to figure out Iy, right? Ohm's law is just Vy over R1 equals Iy. And so then I get this equation. So this is just like the equation at the top, right? Except I want the current going from V2 to V1. So the current going from V2 to V1 is V2 minus V1 over R1, okay? And so you're basically a step away from finding voltages or currents through or across resistors when you have node voltages. And next I'm going to show you, so remember these, I'm going to show you how to use these equations in node voltage analysis. But let me concentrate on this first. Sometimes this bugs folks. Wait, I have an arrow going from left to right for one current, and I have an arrow going from right to left for another current through the same resistor. How the heck could that be? How are currents going in the opposite direction? That can't be, right? Well, it can be, because remember, you can have currents with reference directions that oppose each other, the same current, right? These oppose each other. It's just IY equals negative IX, right? Negative IY goes in the right direction. So I can have arrows facing each other like this. It's just going to be one of those values, IY or IX, is a negative value. You can see that down here in the equation. If you multiply this equation by -1, right, both sides, you get the top equation. And you get IY equals, or IX equals minus IY. Okay, so you can have, so what we're going to do is we're going to use these equations for current in node voltage analysis. So let's do that. Oh, before, let me say this. I said you were 1 or 2 steps away from all other circuit variables. Well, you can calculate power for every resistor once you have the voltages, right? So if I know Vx, or if I know Ix or Iy, let's say from the one step above, this would be step 2 to figure out power, okay, for every resistor. All right, so I'm going to move to the, not the chalkboard, but the whiteboard now. And we're going to work an example on the whiteboard. So let me stop this share. All right, let's get a focus here. Okay, can everybody, let me bring the chat up first. That's funny. I gotta, the chat disappears on me. Okay, so can someone let me know that you can see my whiteboard here? Okay, great. So let's draw this circuit. I like working with a circuit because it's a good example, and it'll be a launching pad for your homework problems. But if I draw the circuit like this, okay, so there's my circuit. And let's suppose, let's use the reference node. Let's define the reference node to be this node at the bottom. And let's give some values to these resistors. Let's say this is R1, R2, R3, R4, R5. Okay, and let's suppose those are known. Those are known values. You know, this is 13 ohms and 86 ohms and 22 ohms, whatever. Those are known values. And then let's suppose I know I sub s. That's an I sub s. So you know those values. It's, you know, -2 amps or 5 amps or whatever. So that's a value. And then I'm going to define node voltages, right? I'm going to say this is V1, just like we did on the slides, V2, and V3. Okay, so those are unknown. Oh, my camera. Oh, my camera stops on Zoom, but it does. I'll start it back up. So the node voltages are not known. Those are what you're trying to find. That's what you want to try to find. Here's how we're going to do that. We're going to write a Kirchhoff's current law equation at every non-reference node. Right? KCL at every. Sorry about that. I don't know why this thing. My video keeps going off. Yeah, try to fix that. So that says we're going to write a KCL equation at every non-reference node. Okay, so what's that mean? We're going to write a KCL equation at V1, at V2, and at V3 nodes. Those are non-reference node, not at the reference node. That's a reference node. Okay, here's how we're going to do that. Let's do this. Let's write at node 1 the KCL equation that corresponds to that node. We're going to sum the currents leaving the node. So I'm always going to use the form of KCL for node voltage analysis, where I'm going to sum the currents leaving that node. So there are 3 currents leaving that node. And so let's start with the easy one. The current leaving through the current source is IS, right? And so that's that current. The current leaving through R2 from V1 to V2, we just calculated that. It's V1 minus V2 over R2. So I'm going to add that in here. Okay. And then the current leaving from V1 down to the reference node, it's the node voltage here, V1, minus the node voltage of the reference node divided by R1. Well, the node voltage of the reference node is 0 volts. So the node voltage of the reference node is 0 volts. And so the next term is V1 minus 0 over R1, right? The current coming from the V1 down to the reference node, that node voltage minus that node voltage over R1. Okay, and so what's that mean? Now we've summed all the currents leaving the node, set it equal to 0. So now we have an expression. And I can rewrite this in a little more friendly way. I'm going to have a coefficient times V1 plus a coefficient times V2 plus coefficient times V3 equals 0. That makes it easier to solve with a matrix or an equation solver. So, so the coefficient of V1 is 1 over R1 plus 1 over R2. And R2. And then the coefficient of V2, right? You get kind of good at this, looking at the reciprocals of resistances. So 1 over R2 times V2 equals minus IS. Okay, so there, that's an equation. It's just a number times V1 plus a number, negative number times V2 equals negative IS. So there is one of your equations for the 3 node voltages. We need 2 other equations. We need 3 equations, 3 unknowns. The 3 unknowns are the node voltages. Okay, so let's do node 2. So node 2's equation Again, I'm going to sum the currents leaving this node. So I'm going to sum the current leaving the node that way, leaving the node that way, leaving the node down. Okay. So let's see. We have the current going from V2 to V1 through R2 is going to be V2 minus V1 over R2. That's what we calculated on the prior slide, on the slide. So R2 plus the current going to the right, excuse me, to the right through R4, and that is V2 minus V3 over R4. Okay, and then the current going down through R3, V2 minus 0 over R3. Sum those currents leaving, set them equal to 0. So I get another equation. So this equation, so let's see, the coefficient of V1 is minus 1 over R2 V1. The coefficient of V2 is 1 over R2 plus 1 over R3 plus 1 over R4. All right, so that's the coefficient of V2. And I'll say, I'll write it down below here. The coefficient of V3 is minus 1 over R4 times V3 equals 0. So we have a nicely formed equation here. Coefficient times V1 plus a coefficient times V2 plus a coefficient times V3 equals 0. Okay, so there's the second equation we need for our 3 unknowns. And so finally, we get an equation for node 3. So node 3's equation, again, sum the currents leaving. It's kind of repetitive here. Sum the currents leaving. So the current leaving through the top branch is negative IS. I'm gonna have to work on this video. I don't know why it just stops on me. Okay, so leaving through the top branch is negative IS, right? And then let's see, leaving from V3 to V2 through R4 is V3 minus V2 over R4. And leaving down through R5 is V3 minus 0 over R5. And those are that's the sum of currents leaving, set that equal to 0. And then we can rewrite this. Let's see, the coefficient of V2 minus 1 over R4 V2. The coefficient of V3 is 1 over R4 plus 1 over R5 V3 equals IS. Okay, so those are the equations. Here's an equation, right? Let me put it by the equation. Here's an equation. Here's an equation. Here's an equation. Here's an equation. And if you solve those equations simultaneously, 3 equations, 3 unknowns, you'll get the answers for V1, V2, and V3. Okay, what's kind of neat about this is you're guaranteed to get enough linearly independent equations for this approach, meaning you'll have 3 equations for your 3 unknowns. So instead of trying to kind of randomly write KVLs and KCLs in a circuit and hoping they're all independent, this is a systematic way to do that. So you just write a KCL equation at every non-reference node, do this, and you get enough equations. Okay, so it's kind of neat that works out. What I like to do, let me just show you kind of in a cartoon equation form here. At this point, you can solve these equations however you want. You can type them into a matrix solver. Many calculators, lots of the TI scientific calculators, you can invert matrices and multiply matrices. I'll show you how to do that. That's what I do. If you have an equation solver in your calculator, you can do that. You can substitute. You can solve these however you want. You were kind of out of the circuits domain into just solving linear equations. The way I do it is so there's a you know, if you look at the form of this equation, you wind up having a set of values. In this case, it's 3 by 3. So in this case, it's 3 by 3. And we would call this the G matrix. Why is it the G matrix? Because the elements of this matrix are made up of reciprocals of resistances. So it's commonly called a G matrix. And then you have values that are of voltages, V1, V2, V3, and that says V1, V2, V3 there. And then that equals this right side matrix, which I'll just call I. Okay, so if you wanted to solve this, you're looking for V1, V2, V3. So you could solve this by saying V1, V2, V3. Okay, that's kind of a column matrix or a vector there, equals G inverse, right? This G matrix inverse times I as a column vector there. Let me just write that like that. Right? So this is a 3 by 1, 3 by 1, right? 3 by 3, 3 by 1. Okay, so this is how I solve this problem. You're welcome to do that. This is easy to do in MATLAB. This is easy to do if you have an equation solver on your calculator, and that's one way to do it. Otherwise, you can plug and chug, or you can enter this into an equation solver. Okay. So this is node voltage analysis. When you're asked to do node voltage analysis, look at the circuit. There's probably a ground defined for you. Keep that, use that, and write a KCL equation using this technique at every non-reference node, and then solve. Okay? Questions on that? Okay. Okay. So you'll have some problems on this, on node voltage analysis. And let's see, what do you set? So I see a question. What do you set equal to each other for the plug and chug method? So you have, for example, let's look at this equation. You have V3 and V2 here. You could solve for V3, right? V3 equals something, and then you could plug that V3 into this equation's V3, right? You could do that, and then you could let's see. You
can't
could,
actually see anything.
oh, I'm sorry. Thank you. That's the kind of feedback I'm looking for. Okay, here is the so here's node 3 is V2. We have V2 and V3. You could solve for this V3 and then plug that expression into this V3, right? That would give you an expression of all V1s and V2s. And then if you wanted to plug and chug, you could, let's say, solve for this V2, plug it into the node 2 expression, and then you'd have the equation in terms of only V1. And once you have V1, then you can plug V1 into the other equation. So that would be like the plug and chug method of doing this. I think that's a little longer. I like the matrix approach because it's just so fast. And equation solver is just as good. So, okay. Is IS given? Yes, IS is a given value. All the resistors are known and the current is known. So V1 through V3 are the only unknowns.
So what about the situation of having just a normal voltage source in there while doing node voltage analysis?
Yeah, that's a good question. Okay, so I'm going to change the problem right now. I'm going to take out this. Let's say I'm going to take out this resistor, and I'm going to draw in a voltage source. This is what you're talking about, right? If I put a voltage source there.
Yes.
Okay, let's say that's 5 volts. Okay, what this has done for you is actually told you what V1 is, right? So it told you that V1 is 5 volts because V1 is defined between, right, explicitly V1 is the voltage between here, that node, and here, ground, and that's V1, and so that voltage source is forcing V1 to be 5 volts. So you'll see that arise in your problems. If this voltage source is connected to the reference node in some way, then that gives you a node voltage. If the voltage source is actually in the circuit someplace else, again, I'll change the circuit a bit. Let's say it's over here. Okay, let's say it's plus minus 4 volts. So what that has told you, that there's an approach to doing this using what's called super nodes. And so we're not going to cover that, and I'm not going to ask you to solve problems like that. But basically what you do is you circle around the resistors where you have a supernode, and you apply KCL to the supernode. And then you insert one other equation, which would be V2 minus V3 equals 4 volts. Okay, so that's how you would do that, but we're not going to actually cover those. It's just kind of like a harder version of what these are. Not that much harder, different. Okay.
Thank you.
You're welcome. Okay, any other questions on this? Okay, so what I would like to do now is just give you an introduction to Thevenin equivalent circuits. Okay. So I've got a slide up now that let me just give you an introduction to this. Thevenin equivalent circuits and maximum power transfer. With all of these linear circuits, Okay, and a linear circuit is any circuit that such that when you connect a source to it, like a voltage source or a current source, it behaves linearly. Its voltage versus current looks like a straight line. Okay, so let's briefly talk about V versus I for linear circuits. So any linear circuit with resistors and sources, either dependent or independent, can be modeled in a certain way. And that way is with a Thevenin resistance and a Thevenin voltage. And we're going to get to that. I'm kind of building up to that. But if you connect a resistor, for example, to any circuit with resistors and sources, dependent or independent sources, and you vary the resistance value, this RL, you're going to see that IL and VL vary also linearly. And so we care about this because there are a lot of circuits out there, a lot of practical circuits that behave like this and are characterized by this, and it makes you easy to connect the right speakers to the right amplifier. And we'll talk about that when we get to maximum power transfer. But for example, your stereo output, your audio amplifier output that goes to a speaker, within a certain frequency range, it actually looks like a linear relationship between VL and IL if you vary RL. Okay, an antenna. So you have an antenna that comes down from your satellite dish into a receiver. That antenna looks like a linear circuit within a certain frequency range. Looks like a linear circuit that can be characterized very simply, and it has an output relationship where VL versus IL change linearly as you change RL. And what that lets you do is this. For those two examples, it lets you deliver maximum power to, for example, your speaker. That gives you the loudest sound and the best quality. It lets you deliver maximum power from an antenna, a satellite antenna, to a satellite receiver. That gives you the best signal to noise ratio. It gives the highest signal for a given noise level. It gives you the best video quality and the highest bandwidth. So that's what Thevenin equivalent circuits is all about. It's determining what is an equivalent of, really a simple equivalent of really just about any circuit that can be modeled with resistors and sources, like a audio amplifier, like a satellite antenna, and it lets you represent that with a simple model. Okay, so before we get into let's hold off on the plots and graphs and equations. I want to let node voltage analysis and kind of this concept sink in for a while. So what we'll do right now is I'm gonna break with class. Thanks for joining the live class again. Again, I hope I hope everything worked out well. I'm having some problems with my document camera. I think Amazon might get that back, and I might get a new one soon. So if there's any other problems, let me know. And definitely check Canvas for the next few days assignments. Make sure, keep an eye on that schedule because these come pretty quickly. So what I'll do is I'll start office hours in about 2 minutes. So if you have any questions, stick around a couple minutes. I'm going to go on mute for a couple minutes to let folks drop off if they want to. So you can either stick around for your questions, or if you want to just listen to other people's questions, you're welcome to do that too. Okay, so thanks for joining the class today, and I'll either talk to you at office hours or see you next time.